Hello everyone, welcome to TryRide, the new era of learning. This is pack 365. Today's module, we're discussing about breadth-first search, algorithm AI, part B. Let's move to the topic. We all know that yesterday's previous lecture, we discussed about BFS. So in this lecture, we discuss somewhat wide range about it. So what is breadth-first search? Breadth-first search is a fundamental graph traveler algorithm, right? It begins with a node, right? It begins with the nodes. Then first traverses all its adjacent nodes. Once all the adjacents are visited, then the adjacents are traversed. Like if the one we move one edge, one vertices, if it is we covered all the vertices of the graph without forming any loop cycle. So that is the BFS. Want to visit all the adjacent without forming a loop, right? Then the adjacents are traversed. So BFS is defined different from DFS in a way that closest to verticals are visited before others. We mainly traverse verticals by level. We used to travel the we have level by level which nodes are connecting to the visited node. We travel from the to one node to another node by checking the levels, like we are removing by using this technique of first out before. And popular graph algorithms like Discus and shortest path and uh, Khan's algorithm and Prim's algorithm are based on uh, same the pattern like BFS, like. And the BFS itself can be used to detect cycle in a directed and undirected graph, right? Find the shortest path in a unweighted graph and many more problems. Like if we if the we are starting stage two, we are moving to next vertex to next level. So we observe the vertices, right? We observe the vertex, which will if you move A to B, if it is in the between the parameters, it will the connection between the connections. If the we travel A to B, if it is forming a circle, so it doesn't go to a B. It visits an other way. It returns back to the way because it does not want to form a cycle to in the graph. So now we take a bit for such or BFS for a graph. So give a undirected graph represented by an adjacent list. Like we are taking example graph, given a undirected graph represented by an adjacency list, ADJ, where each ADJ one represent that list of vertices connected to the vertex, right? Vertex I. So perform a BFS traverser starting from vertex 0, visiting vertex from left to right according to the adjacency, right? List. And return a list containing the BFS travelers of a graph. So we are taking a graph example. So we are containing adjacent AD list as ADJ, and we have vertex as I. We are return back to right according to the adjacent list. So return a list containing the BFS travelers graph, right? So we have inputs, adjacent like 1 comma 2 2 0 comma 2 3 0 comma 1 4 1 4 and 2 3. We have like input. So from the we have a graph. So we have a graph, like we have inputs like 0 1 2, all are connected graph, right? So from this connected graph, we want to make BFF. Like BFF, we don't want to form any cycle or any loop from this. Okay. So we have a diagram. So first, we want to print the output. Output has 0 1 2 3 4. I will explain this structure in code and extra in theory type. Don't worry about the code. I will explain it also. So output 0 1 2. We want to print the output as 0 1 and 1 2 3 4 like that. So explanation starting from the 0. Okay, it's starting with the vectors is 0. The BFS traversal will follow those steps. We have some few steps. We step one like visit 0. Output will be 0. If we visit 0, output will be 0. Next visit 1. First neighbor of the 0. We have first neighbor of the 0 as 1 and 2. We have both neighbors. So it picked 1 as a neighbor. So enter in the quiz queue and visit 2. Next neighbor of the 0. Next neighbor we have 2, right? We have both neighbor 1 and 2. So we enter the neighbor in the queue 2 also. And visit 3. And the next neighbor of the 1 is 3, right? We entered the 3. Then we move to the 3. And next, the neighbor of the two, we have two, we have one neighbor has three and two neighbor has four. Like we want to enter the, then if I get the final output like 0, 1, 2, 3. So step what we're performing, first neighbor of the 0 is 1 and the next neighbor of the 1 is 1 and 2. We have both neighbors. For the 1 and 2 we consider in the list, and after the next neighbor of the 1 we have 3 and the next neighbor we have 2, we have 4. And we get the final output. So now we can see here maintaining a quiz, like we can see here in a other format too. So maintain a queue, res and visit arrays. Okay. So visited arrays, we have three structures: visited, res, and queue, right? Which we are entering. So such that the queue store nodes to be processed in FIFO order. Like in FIFO order, we are putting first in first out to RES for storage of the BFS traveler sequence, and visited keeps the track or visited nodes to prevent the processing, right? So we have the graph. Let's move to step. So we are in step two. It started with 0. So in visited, it make mark as T. Started the traverser with node 0. Push it into the queue 0. We entered a mark it has visited. We mark it has visited. We have so, and while the queue is not empty, pop the front node to the store. Like we have 1 and 2. We enter the next step. Like we entered the 1 and 2 here. Like the sequence is like that. The according to color we're processing. So from the color 1 and 2, this is 1, like this is 1 and this is 2. Like we enter the color like 1 and 2. We visited like we my making mark has visited has T. With denoting T mark, we are visiting like that. So we enter the mark has 0 and 1 and 2, right? 0, 1, 1, we visited 0 and we left over the 0. We moved the next piece to 1 and 2. From next tick, we have one neighbor, 3, and two neighbor as 4. Let's move to the next graph. Here we can see, we visited, we left over the green, zero, right? Remove the front element of the one, like what element we have was zero, and we remove zero from the piece, we visited it, and we increase from the quiz store the in rest, like we remove it and we store it in one, like it is the output part. We visited zero and we left over zero and we entered in one, right? In the quiz we remove the one, right? We are stayed in one. So the next order of the one is two and three, right? We have two entry of the one. We enter the into the quiz. So already two is existed in the quiz. Sorry, already two is existed in the quiz. So enter the three. So visited its unvisited neighbors, mark them as visited, right? We mark them as visited and push them into the queue for the further process, for the next process. So here we entered in it and after we marked it and we left over it. Okay. So visited. Next step. So right here you can see we left over the one also. We marked it as one as visited and left over visited, and we have visited now two. So from the two, again, we want to remove the elements like we have visited as T. We want to visit the neighbors of the two is 3 and 4 only. So we already existed a part of 3. So let's move the part like we visited 4 front, like okay. So remove the front element 2 from the quiz because it stores in the rest. Visit it unvisited. Visit it has it unvisited neighbor and mark them as visited, right? And push them into the queue from the further process. Now it directly goes to 1 and it moves to 3. It get back to the 1 because if we form we did not have next circle 3 to form like we did not have any connection to 2 to 3, so it go back to the 1 and it go back to the 3. It visited 3, so remove the front element 3 from the quiz, store it in the rest. Visit it is unvisited, like same the process we are following. All the nodes of 3 have visited. uh, pro- Proceed to the next node in the quiz. Like we are next, we enter into 2 and we remove the 2 has already visited. Then we move to the 3. Next to next line, next of the line visited. We want to visit the next sequence, right? So visited 3 here. So left over 2 because we already visited it. Now in present position is 3. So same the step is reported. So up to empty of the vertex, right? We all left over the 3. We entered the 4. Now We visited 0, visited 1, we visited 2, and we visited 3 also. And final visited 4, right? Up to the 4, all nodes of the 4 have been visited. The process to the next node in the quiz, right? So moving to the next, so the quiz is empty here. So we can see we all the 4 also get removed. Now we entered the 4, it also visited. So we have completed our visited, right? We have completed all the quiz here. Now that is a quiz is empty and there are no more nodes to process, right? We obtain the final BFS travels for here. So we can confirm here, we visit all the nodes step by step. So the final node could be 1, 2, 3. Visit like 1, 2, 3, 4. Like we have visited the vertices, right? So now coming to the point of application of BFS in the graph. So we have application of shortest path finding. BFS can be used to find the shortest path between two nodes. It has an unweighted graph by keeping the track on the parent of the each node during the traversal. The shortest path can be reconstructed, right? So shortest path finding is nothing but it is an unweighted graph. Okay, so it is uses like to find the shortest path from a source of node or to all the other nodes in an weighted graph, right? So because BFS explore all the nodes level by level, the first time it reaches a node, it chooses the shortest path, least number of the edges, like that. Finding shortest path, like in map, maze, or game level. So cycle detection. BFS can be used to detect cycle in a graph. If a node is visited twice during the travel cycle, it indicates the presence of the cycle. Like it used to check the whether a cycle exists in the undirected graph or not. So during the BFS travels, if you encountered a visited node that is not for a parent, and it means that it is cycle. If it does not forming a cycle, you can move forward. So, connected components. BFS can be used to identify the connected components in a graph. Each connected component is a set of nodes that can be reached from each other, right? So, it uses to identify all the connections of the component in graphs. Okay. So, however, it uses like run BFS from every unvisited nodes. Each BFS travels which we will visit one connected component, right? So finding the isolated groups, like examples in social media and subnetworks, we joining the communication networks here. So we have a topological sorting. BFS can be used to perform the topological sorting, a directed a cyclic graph DAG. So topological sorting arranged the nodes in linear order such that for any edge UV, like you have U appears before V in the order. So we can say that it used to start node, sort the node in a directed we use in a DAG like a directed acyclic graph, right? Such that for every directed edges, U to V, U comes before V, like that. So in this, how we use like we use here, we already discussed about the KHN as like Khan's algorithm uses of BFS, and in degree counts that determines the valid topology order. It follows the orders. So level order traversal of binary trees. BFS can be used to perform a level order traversal of binary trees. This traversal visit all the nodes at the same level before moving to the next level, right? So it uses to travel a binary tree, level to level from the top to bottom, like that. So top to bottom, like right to left, like it used to travel like that. BFS apply it uses the bit first is applied using a quiz used to apply the quiz, right? So visited all the nodes at the each depth before moving to the deeper. Like we have lost concept last application as network routing. Like BFS can be used to find the shortest path between the two nodes in a network, making it useful for routing data packets in node protocol, right? So it is nothing but to find the efficient route path. It used to show okay to which is network routing is nothing but to find the efficient route path in computer networks. Like in the unweighted networks, BFS helps to determine the shortest route between the nodes, right? Okay, to switch the next state. So I hope you guys all are understand about the topic which you know which we discussed now. So part B. So thank you guys.